A force F is used to move a body of mass m up a hill. At each point on the path, the force is along a tangent. We're asked to find the work done by this force. The height of the hill is given as h and the length of its base is L. The coefficient of friction is mu. So here, if I look at what is said in the question says that the body is moved very slowly. So whenever any object moves very slowly, so we can say that the change in velocity is 0. Okay, so the body is moved really slowly, so the speed is good enough for the body to move up the hill, but there is hardly any change in its speed. Now, if I look at the other forces that are acting on the body, we can notice the gravitational force obviously acting in the downward direction, and opposite to the direction of motion there will be friction. Now this friction is kinetic friction. So if I take the gravitational force, that's mg, and the friction forces, in this case we can take it as mu times normal. Now because the change in velocity is 0, the change in kinetic energy will also be 0. So if we apply the work energy theorem, which says net work done by all the forces is equal to change in kinetic energy, the right hand side is clearly 0. So what do we have on the left hand side? We have work done by the applied force plus the work done by gravitational force, G stands for gravitational force, plus the work done by the friction force. So this amounts to 0. So now let us see how we can calculate the other two forces. So the gravitational force points in the downward direction and the body displaced upwards by h. So clearly the work done by gravitational force is negative and the magnitude is mg into h. Now let us see how we can calculate the work done by friction. Now to calculate work done by friction, what we can do is we can imagine a tiny patch on the path. Let's say this tiny patch has a length delta s, and horizontally its projection is delta x. Now if I enlarge it, I can treat that this tiny patch as an incline. Okay, so I have delta s, and then we have this object on that incline. Now if the angle of inclination is theta, the horizontal projection delta x can be written as delta s into cos of theta. Now while the body is moving along this tiny patch, we can get the magnitude of friction force by considering the force, which is mu times normal multiplied by delta s. And then we know whenever an object is on an inclined plane, if the angle of inclination is theta, the normal force in these conditions is mg cos theta. I think this is something that most of you know. You can imagine that this tiny patch is somewhere here. So I can take this angle will be theta, and then I can take a component along the line perpendicular to the trajectory. So that is mg cos theta. So I can write this as mg cos theta, and then multiplied by delta s. Now if I take this delta s and cos theta together, what we get is mu mg into delta x. Now this is the work done along a small patch whose horizontal projection is delta x. So you can see that if you add up the entire work done by friction force, I can just write the magnitude of friction force as, let's say, the sum of the magnitudes of friction force. I can write it as everywhere you have anyway mu mg, and then we can keep taking this horizontal projection. So delta x1, let's say, suppose, and then another tiny patch is delta x2, and so on. Okay, so the sum of all these delta x's is obviously L. So we can write the work done by friction force is mu mg into L, and obviously the force is opposite to the displacement each time, so this is negative work, so this is equal to 0, and then we have work done by the applied force. So from here we get the work done by applied force as I can take mg as a common factor, and then I have h plus mu L. So that is the work done by the applied force.